Hello, my name is Rob Garner. I'm a computer programming instructor, and today I'm going to demonstrate how to declare variables in C++. So to begin, open Visual Studio, and we're going to create a new C++ solution and project. So new project. And make sure you selected Visual C++, empty project, and we're going to call it variable declarations. I'm going to store it on my desktop and click OK. Once your project opens up, let's make sure first that it'll run properly for us when we run without debug. And what I'm going to do is check my project by right-clicking on it. Note that this folder is the project, the one above it is the solution. So we're right-click on the project, click on Properties, and then under the linker and under System, I'm going to set Subsystem to Subsystem Console. This just makes sure that when we run without debugging, the console window won't close before we can see what's happening. Next, we're going to add, click on the source files folder, we're going to add a new item. We're going to make sure we have Visual C++, C++ file, and we're going to make a new file called declaration demo and click Add. This creates a declaration demo file under source files and opens it up over here. Again, remember, if you lose it, you can just double click on declaration demo and it'll bring it up. And now we're going to write the beginning of our program. So we're going to include the IOStream library so that we can send output to the screen and get input from the keyboard. We're going to use namespace standard so that our program will be differentiated from other program names. And then we're going to declare our main method. This is the method that the operating system will run at the beginning, and in order to tell the operating system that the method has run successfully, we will return 0. So this code here is something that's not bad to memorize because all of your console programs will generally start off with that. Next thing we're going to do is add some comments. Comments are important because they help other people understand your code. They may have to maintain it, and actually you'll find that after about a year you don't remember what you wrote, and so they can help you understand your code after a period of time. So I'm going to put the program name. I put my name, and normally in this space I would have my email address. The date, and a purpose statement. And usually in here, really communicating normally to the user, to the programs, why this was created, and sometimes you might include information in here if specific things need to be done in order to use your program that you're creating. Now this is called a block comment, and really the only things that designate as a block comment are this first slash and asterisk and this last asterisk and slash. And basically between those two designators, the compiler ignores everything between them. And so you can write anything you want in here and format it any way you want. And so those block comments are good for large comments. If we just want to make a single line comment, we just use a double slash and write our comment. With a double slash, everything's ignored from here to the end of the line. So anything you put after that will be ignored. The next step we're going to do is we're going to create a demonstration that shows that capitalization is not. The next thing we're going to do is demo that capitalization is important in C++. And to do that, what I'm going to do is I'm going to declare two variables, one which has an identifier that's all in lowercase, and one where the identifier is all in uppercase. And you're going to see that I've assigned two different numbers to it. And we're going to use cout to display total. And I'm going to put a/n at the end so that we can see the result. And then the capitalized version of total. So what will happen is we'll declare a variable total with lowercase equal to 5, another variable total with an all uppercase equal to 10. And you can see if these were the same, we would actually get an error. For example, if I tried to declare total all lowercase a second time, both of these would be 10. But if I declare it this way, we're going to see that they are not the same variable. So if I run this, what we can see is that total is represented as 5, total is equal to 10, and they haven't overwritten each other. If these are the same, both of these would be 10. But these are in fact two separate variables. So despite the fact that they're the same word, the capitalization differentiates them. So make sure you keep your capitalization consistent. Another way we can kind of demonstrate this is if I put cout, and let's say that I had one that was Pascal cased, which means that it starts with a capital letter and then the rest are lowercase. We can see that it doesn't recognize this third one. Total is undefined. So total with a capital T and all lowercase is not the lowercase one or the uppercase one. This is important because it's very easy to miscapitalize things periodically, and that will create an error. So what we're going to do is I'm just going to comment this one out. Commenting out of the line is a common programming technique. If you haven't sorted something out yet, sometimes you comment out of line during debugging in order to temporarily take it out of play. The next thing we want to do is demo that the compiler doesn't care about character turns. So if I were to declare an int called myVariable and set it equal to 15, for example, and then displayed it, we're going to declare my variable as an int. We're going to set it equal to 15, and then we'll display it. Actually, just to make it different, let's make this a float. So I run it, let it build, and what we see is my variable equals 15, so that works just fine. But I could equally, well, do this. And so here I've broken it up onto separate lines, and if I run it, we can see that it still runs. This still sets that variable equal to 15. So it really doesn't matter about the line space. In fact, the compiler ignores all of the spaces. We could even write everything on one line, except for the comments. And we see that it runs the same. Of course, this is somewhat difficult to read, so we don't like to write our code that way. So we'll put it back to the way it was and continue on from there. Next, let's add some more declarations. We'll declare a char. A char is used to represent a single letter. So we put one single character between two single quotes. You don't want to put double quotes because it'll give you an error. And in this case, value type constant char cannot be used. Initialize entity of type char basically means we can't use the double quotes. We have to use the single quotes. Another thing with chars is if you put two values in there, it will actually work, but when you build the project and it compiles, we'll get some warnings, and we'll see that it says truncation from int to char, and what that looks like. Normally you would think that this would be A and B, but when I run this, it actually, letter of alphabet becomes B. It actually gets rid of everything except for the last character. So what we want is just one character when we declare a char. and we can see now that letter of alphabet is A and is what we expected it to be. We'll declare an int 25. And display that. We'll declare a float, which is a floating point number. It means it can have a decimal point, unlike an int that can only have a whole number. So, not a bad way of storing a bank balance. And a double, which we can use to store an even higher precision number, more points after decimal point essentially, and we'll use this to store a very small number. And we'll create a Boolean. Booleans store true false numbers, and typically by convention we will precede their identifier with the letter B. And they can have the value true or false. And so we have our variable declarations, and we're displaying them with couts. Notice that we don't have any errors, so these declarations look like they're going to work. And if we look at these, we can see that everything worked pretty much as we expected. The integer, which is called a whole number, displayed 25 as we expected. The bank balance, which displayed 500.5, which is what we expected. It's a floating point number. Notice though that the double, which we made very small number, actually was displayed in scientific notation. And the way you can read that is whenever it says 1e minus 0.18. That 1 corresponds to this 1 down here at the end of the small number. And then the e you can look at that as times 10 to the minus 18th power. So that will give you 18 decimal points past 18 positions past the decimal point. And that's how scientific notation allows us to record very small numbers or very large numbers. And then our Boolean, notice that we set it to true, but it displays as 1. And the reason for that is that it represents Boolean numbers as a 1 or a 0, and when we display it here, it actually renders itself when we send it to cout as a number. So the next thing we're going to look at is a little bit more on the char variable type. The char variable type, even though we represent it as a letter, is actually a number. So we can actually declare, say, letter A is equal to 65. And when we send this out to cout, So when we send letter out, CA to C out, let's see what this actually displays. So after hitting Control F5 and compiling, what we notice is that letter A is displayed as an A, but we put it in as 65, so why doesn't it display it as 65? Well, in point of fact, 65 corresponds to the ASCII code of A, and so here's a chart which shows the ASCII code, and if I find 65 on here, we see that 65 corresponds to the letter A. And what C++ does is whenever you just send a char to C out, it's actually going to look it up in this table and display the character representation of it, not its actual numeric representation. So that's why 65 becomes A. And if we were to change to 66, it would become B, 67 would become capital C, and so on. In order to figure out what it will be, you look at the ASCII chart. So the next thing we're going to look at are max and min values. It turns out that memory locations can only store so much numbers of a certain size. If you exceed that size, you get unpredictable behavior. So for example, an int, the largest that an int can store is 214,748,3647. And no, I don't have that memorized. You can look those up online, and there's typically charts in most computing books that show what the largest and minimum numbers are for a particular variable type. So if I run that, I can see that the number displays what I expected. Largest is 214,474,83647. So that worked. Now suppose I were to display a number 1 larger than that. And we're going to call this variable toLarge, and I'm going to add 1 to that number, so it's 1 more, and then we'll display that and see what happens. Well, what happens is we see that toLarge is displayed as a negative number. It's the opposite of what we thought it would be. And in point of fact, if you exceed the size of a number, unpredictable things happen, and it doesn't give you a compilation error. It happens at runtime, which is unfortunate because you won't be able to figure out that that's happening until it's too late. One way to look at this is if you open up the calculator function that's provided to you by Windows, you can actually normally it looks like this, a standard calculator, but you can put it in the programmer mode, and you have the opportunity to operate in decimal or binary. So if we take our the original number, and look at it in the calculator, and I convert that to binary, we can see it's all ones. And down here we can see what it is broken up into 4-bit chunks. And so in memory it kind of looks like this. And you notice that there's this that 1, 2, so that's 1, 2, 3, 4, 5, 6, 7, 8. So that's a 32-bit number. So an int is a 32-bit number, and you notice that with the positive number, the most significant bit, the last one on the left here, is a 0. And in point of fact, what the computer does is it uses this most significant bit as, or least, well, the most significant bit as the to indicate the sign of the number. So if it's 0, it's a positive number. If it's a 1, it's a negative number. If I add 1 to this, we see that what happens is when we get this large number, it adds 1, everything becomes 0, and 1 gets added here. Well, if this is a sign bit, now this is interpreted as a negative, and this whole number here is then interpreted as that maximum value. And that's why when we run this, this turns into the largest negative number, as opposed to, or the greatest magnitude negative number, as opposed to the largest positive number. So it's a good idea to, when you're programming, to look at a chart like this, which shows all the different types of numbers and then their maximum and values. You'll also notice in this chart that we have this unsigned keyword. And what that does is it allows us to create a value that goes from 0 to largest value. And you can see here, if I look at an unsigned int, it's 0 to about to 4294 is 967 295. But an int goes from minus that number to that number. It turns out that this number is twice as large as the maximum value. So it's storing the same amount of information. It's just that when we go unsigned, it doesn't use that most significant bit to record, to identify whether it's a positive or negative number. It throws that into the amount of bits that we can use to store information. So let's do something with the unsigned notation. So in this case, what I'm going to do is change this code up and demo unsigned int. So we'll call it, and the largest is actually is twice that. So we'll put in 4294967 if I type that in correctly. And the one that's too large is +1, and we're going to change these to unsigned ints. And I'm going to change their name to largest unsigned int and too large unsigned int, and we'll display these things so we can see them. And let's run that and see what happens. And if we look at this, we can see that largest unsigned int goes to works correctly, but when we add 1 to it, it goes to 0. And again, it relates to what's happening at the binary number. So I'm going to subtract 1 to get us back to this largest value, and we can see here, well, actually, if I add 1, so if we look at our calculator and we paste that new value in, so that's our largest int. And if I convert that to binary, what I see is it fills up everything with ones. If I add 1 to it, we can see that we lose. It puts zeros and everything and puts one beyond the most significant bit. Since there's no place for that 1 to go, it just gets thrown away, and then it gets represented as a 0. So that's why when we run this, we get a 0 instead of 1 more than the maximum value. This actually resulted in a launch failure of an Ariane rocket on a while back. Back in 1996, June 4th, they launched the Ariane 5 rocket and exploded approximately 40 seconds later. And the problem is that they did a type conversion error. What they did is they had their horizontal velocity represented as a floating point number, and as the rocket was pitching over, the horizontal velocity kept increasing until it was about 32768 probably, and so we can represent that with this floating point number equal to that. Then the next thing they had was they had a short int, a 16-bit integer, to represent the velocity in a calculation. And they took the horizontal velocity as the float, and they converted it into this integer. Well, at 32768, it turns out that a 16-bit integer can only store a value of 32767. And when you do this operation here where we assign it into, when you assign a float into an int, if it's too large, the following happens. And we can see that the horizontal velocity of 32768 in the float becomes a negative value in int velocity. So if the rocket thinks that it's going in the opposite direction across the horizontal plane, what it does is it actually completely reverses at 90 degrees its flight of travel and explodes in the air. So this is why it's important to pay attention to variable declarations and the maximum value of the types that you declare. And that completes my demonstration. Thank you.